this presentation. We are starting the series of questions and answers on acid-base equilibrium. Let's start on question number 1. Question number 1 is saying, what is the pH of 0.75 molar sulfuric acid, the dissociation constant, which the second dissociation constant was given? That means the first dissociation constant was not given because it is a strong acid which is fully dissociated in the solution. Let's see the answer. Sulfuric acid is polyprotic strong acid because it has 2 protons. So, and on the first, it will have a full dissociation in the water. The first dissociation here is complete and no need of the dissociation constant. That's the one it was not given. So first dissociation, we have the sulfuric acid which will dissociate to give the first proton and to give this HSO4 minus. So this is the concentration of H plus. It will be equal to 0.75 molar. That means the concentration plus H plus will be equal to the concentration of the acid. And also it will be equal to the concentration of HSO4 minus. So that is what you have. Concentration of this one will be also equal to 0.75 molar. Then on the second dissociation, this one, HSO4 minus, which is this one, is going to dissociate to give the hydrogen and sulfate ion. That means the second dissociation will involve dissociation of this one, which will give H plus and sulfate. Here we have the Ka2 because we have the second dissociation that will be equal to the concentration of H plus times the concentration of sulfate dividing with the concentration of HSO4 minus. After the first dissociation, we have 0.75 of this one, 0.75 of H plus and 0 sulfate. Then in the second dissociation, that's where the sulfate is going to form. The second dissociation will involve this one. That's why we put negative X. This one will be removed. The H plus will be formed and the sulfate is going to be formed. But H plus, remember, there is also 0.75 H plus dissociated from the first dissociation. Here we have a common ion effect. That means this X, which will be dissociated from the second dissociation, will be very small. Then K2 will be equal to this one, X, 0.75 plus X over 0.75 minus X. So that's what we have. K2 we have, here we have it. So that is the sulfate, which is X, and you have the H plus, which is equal to 0.75 plus X, and you have the HSO4 minus, which is equal to 0.75 minus X. So if you can assume the denominator, this X in the denominator is negligible as compared to 0.75, then that means this will be negligible. We have this one. Then X will be equal to 0.011 molar. But we need to verify whether our assumption is valid. Assumption is valid if the percentage dissociation is less than 5%. So we can get percent dissociation. We take the one dissociated, 0.011, dividing with the initial amount of H plus, the initial amount of HSO4. Then we have the 1.46% dissociation. Here the percent dissociation, you take the one dissociated dividing with the initial amount of HSO4 minus, you can also is the same as the H plus. So then here we have 1.46, you can see it is less than 5%. In this case, the assumption is valid. Then to calculate the pH, we need to add the 2 hydrogen, the one dissociated from the first dissociation and the second dissociation. If we add them, then we get 0.761 molar. In this case, we can get the pH which is equal to negative log H plus. So which is negative log for this value, then we get pH is equal to 0.119. That was the pH which was asked on the first question. Let's see now the second equation. asking, it is saying calculate the concentration of each species present in 0.01 molar solution of phthalic acid. The concentration of phthalic acid was given, and the K1 and K2 for phthalic acid was given. This is K1 and this is K2, so they were given K1 and K2. Now they are asking at equilibrium what will be the concentration of each species. Then here, check, we have two carboxylic acid group, 2COOH. That means the first one will dissociate, and in this case we use the first dissociation constant because it is the one which is higher. The second one is also going to dissociate, and we use the second dissociation constant. So to know which function group is the one dissociating on the first time, so we use the Ka value. That means the one which has the Ka value which is high is the one which is going to be dissociated in the first round. So during the first dissociation, we have a proton from the OH group will be bathed in the solution, and that is what will happen. We have this phthalic acid which will give this one and this one. Then we can calculate how much this one dissociated from the first dissociation. Then the second dissociation, this one is going to dissociate. The second dissociation, that's the second COH group, that means this one remain dissociated. We also dissociated, liberating the proton in the solution. So this is what will happen here. This one will also dissociate to give this one and this one. We have the Ka2. Because the dissociation, the second dissociation will be negligible because we will be having the common ion effect. Because we have the hydrogen dissociated from the first dissociation. Then the second dissociation is very small because we are having the common ion effect, because there is already hydrogen dissociated from the first dissociation. Let's start from the first dissociation and see what will be the species remaining. That means this one will dissociate to give this one plus this one. This is the Ka value. That means we have 0.01 initially. Here we have 0 and here we have 0. Negative x, here we form x and here we form x. We get 0.01 negative x and here we have x and x. That means the K1 will be equal to the reactant over the product of reactant. That means x times x over 0.01 minus x. Remember here, the Ka, the constant, we take the product of reactant. And this is what we will have if we assume x negligible. In this case, we are going to have the x is equal to 0.0032. That will be the concentration of hydrogen which will be dissociated from the first round of dissociation. It will be equal also to this one, and this one which will remain undissociated will be equal to 0.1 minus x. But the assumption that we need to verify the assumption by calculating the percentage dissociation. And we will see that here the percent dissociation is 3.2%. So our assumption is not valid. We need to go to the solving of the quadratic equation. How this one is obtained, we take the one dissociated, 0.0032, dividing with the initial 0.01 times 100. So assumption is not valid since the dissociation is higher than 5%. We use the quadratic equation to solve it. That means we need to find the quadratic equation, and if you go quickly, you will find this quadratic equation that we need to solve, and we determine the determinant. After determining the determinant, we determine the square root of the determinant, we obtain this one, then you obtain the x1, which will be rejected because the concentration cannot be negative. We have also x2, which is equal to 0.0028, that means that one needs constant. Then the hydrogen dissociated from the first dissociation will be equal to 0.0028. That means this term will be equal to H plus it will be equal to 0.0028. This is the hydrogen from the first dissociation. Remember also this one is going to be dissociated on the second round. Now we have the concentration of H plus, which will be equal to concentration of this one from the first dissociation, and you are going this one they are going to change. Why there's a value they are going to change? You cannot keep this value because the H plus will change because this one will dissociate again to give H plus. This also is going to change because it will dissociate. So that means that at equilibrium we are not going to have this amount of H plus and we are not going to have this amount of this compound because they are going to change in the second dissociation. But we have the one which is not changing at equilibrium, which is the undissociated the acid, which will be equal to 0.01 negative X. So that means you have 0.0072 molar of undissociated the acid. This one will have it at equilibrium because on the second dissociation it will not dissociate, it will not change. That means now so far you have the one species which will be present at equilibrium, which is 0.0072 molar. Let's go to the second dissociation. That means the second dissociation will involve this one changing and this one changing because this one will dissociate to give H plus, the H plus they are going to be increased, and this one also will dissociate and it will go to good, it will decrease. Let's go quickly and see. So the 0.0027 molar is the concentration of undissociated acid and will not change in the second dissociation. This one does not involve the second dissociation. Let's see the second dissociation. So this one will dissociate to give H plus, and this one we use the Ka2 that was given. So we use the IC table. From the first dissociation we have this concentration of this one. We have also the H plus, we have also this one, and this one we don't have from after the first dissociation. But this mixture that we have, this one will dissociate to give H plus and to give this one. That's why this one will be removed. This one will be X plus X because we are forming this one, we are also forming the H plus. Then at equilibrium, how is this one minus X, X, this one plus X, then we can solve for X. So that's what we are doing. Assume X negligible here, we are making the X in the denominator negligible. Then in this case we have the X which is equal to this one. What is X? That's the hydrogen dissociated in the second dissociation. But the total hydrogen will be equal to this one plus X. This one is the one dissociated from the first dissociation, and this one is the one from the second dissociation. Here, assumption is valid because the percent dissociation is less than 5%. So the partial dissociation is valid. Now we have the X, which is the hydrogen dissociated from the second dissociation as 3.9 times 10 power negative X negative 6 molar. So that means the species that will be having after the second dissociation will be having this one, which is equal to 3.9 times 10 power negative 6, and we have also H plus, which will be equal to this one plus this one. You can see that the X, the hydrogen dissociated from the second dissociation is negligible. That if you add it on the first, then you don't get any change. Then after getting the total H plus, you can determine the hydroxide, which will be in the solution at equilibrium. Then you take 10 power negative 14 dividing with this one, and you get 3.6 times 10 power negative 12 molar. Then this one, so the one will remain after the second dissociation, we get this one minus X, and we get this value. So concentration of each species present, so we have this one, we also have this one, which is this one, we also have this one, and we also have this one, and we have also the hydroxide. So these are the concentration of each species that will be present at the equilibrium that was asked. That was question number 2. Let's quickly move to question number 3. They are saying quinine is a base with a chemical formula. This one calculate the pH of quinine, a diprotic base with a concentration of this one. The KB1 was given and KB2 was given. So that means quinine is having 2 nitrogen is a base. That means there's 2 nitrogen. They will attract the hydrogen, liberating hydroxide in the water. So the KB1 and the KB2 were given. So the first dissociation of hydroxide is the one which we will use, this one with a high KB5. Then the second dissociation we will use the KB2. So let's see the answer. So a base will attract hydrogen from the water, and hydroxide will be liberated in solution. So that means that's what will happen. We attract the hydrogen from the water. The first nitrogen will attract hydrogen from the water and giving this one and this one. Then on the second dissociation, this second nitrogen is the one which will attract the H plus also from the water. So this is how the quinine looks like. This is the first nitrogen, this is the second nitrogen. That means that's the reason why they are saying it is a base, and it will have two dissociation because it has the two nitrogen. So here then we will proceed with the dissociation. So that is what will happen. This is the first dissociation, and the KB1 will be equal to this one, the product dividing with the reactant. Now the first dissociation, initially you have this one, we don't have this one, and we don't have hydroxide. Then the change, negative x, and X. Then we have this one minus X, this X will be formed and X will be formed. Then X will be equal to the hydroxide dissociated from the first dissociation. If you assume X as negligible, then we can have the X is equal to this one, 4.02 times 10 power negative 5 molar. Then the percent dissociation will be equal to this one. So assumption is valid because the percent dissociation is less than 5%. Now we have the X from the first dissociation, or the hydroxide from the first dissociation. Then the second dissociation occurs when they resolve the hydroxide ions to the first dissociation. That means we have a common ion effect. That means the first dissociation we have the hydroxide which were liberated in the solution, and the second dissociation will come, and after it will find that there is the other hydroxide which are in the solution. Here we have the common ion effect of hydroxide. So after the first dissociation, you have this one and you have this one, you have this hydroxide, and you have also these terms after the first dissociation. Then this one will dissociate in the second dissociation, also liberating the hydroxide. So in this case, you have this one, you have this one, the change. That means this one will dissociate, forming this one, and forming also other hydroxide. Then we have this one, and this one. So we have the K bit, which is equal to the product, can you see that, plus X. This is X dividing with the reactant. Then this hydroxide, that means the X is equal to hydroxide from the second dissociation. So this is what you have. We can either solve the quadratic equation. Yes, you can solve the quadratic equation. We reject and we get this one, no OH again, the second dissociation. If you do the quadratic equation here, you get 0. That means the second dissociation will not provide any hydroxide. That means the total hydroxide will be coming from only the first dissociation. So then we have a pH equal to 4.4 and we have pH is equal to 9.6. So you can also use this term negligible. If you don't want to solve the quadratic equation, you can make this term negligible, and then you also verify the assumption. You can also solve the equation by assuming X as negligible. If we make the X negligible, we will see the percent dissociation is this one. So that means the assumption will be valid. So in this case also you get the same answer. You get 9.6 as the pH. For those who don't want to solve the quadratic equation, then you can use this one. You make the X as negligible and you verify whether your assumption is valid. Now let's go to question 4. Question 4 is saying what is the pH of 0.1 molar sodium hydrogen sulfate solution, sulfuric acid, the strong acid, and the pK2 of HSO4 minus is 1.92. Here we are asking to calculate the pH of this salt. Of course, this HSO4 is the one which is going to be dissociated. The sodium plus is the spectator ion. Let's see, of course, this is salt coming from a strong acid, because sulfuric acid is strong acid. That means sulfuric acid will give a weak acid after dissociation. So that means we have HSO4 minus the weak acid that will be dissociated, giving H plus, and the pH will be governed by this H plus dissociated from the salt. So here then we use the IC table. We have 0.1 of this one. Here we don't have, and here we have 0. Then we determine x, that is how much hydrogen dissociated, and here, so we get the quadratic equation. Solve the quadratic equation, or you can assume the x negligible here. If we assume x negligible and verify the assumption. So here, if we make the x negligible, that's what we get. We are making here the x negligible, and then we are going to get the percent dissociation equal to 34.7%. That means the assumption is not valid. Here we need to use the quadratic equation. So the percent dissociation is higher than 5%, so assumption is not valid. We need to solve here a quadratic equation. This is now the square root of determinant. We have determined the determinant. This one will be rejected because it is negative. The concentration cannot be negative, and x2 will be equal to 0.029. That means the hydrogen from the second dissociation will be equal to 0.029. So that is the pH will be equal to negative log H plus, which is equal to negative log of 1.54. Negative log of 0.029, which is equal to 1.5. That means the pH will be equal to 1.5. So you can see here, it is a salt coming from a strong acid. Strong acid, then that salt will be dissociated, as you can see, and you get the pH is equal to 1.554. Let's move to question 5. Question 5 is saying calculate the pH of solution containing this amount sodium 2HPO4 that has been dissolved in this amount of water, phosphoric acid, the weak acid with Ka1, Ka2, and Ka. So phosphoric acid, the weak acid. So the salt that will come from the weak acid, they behave as both as acid and base. So then you need to check whether this salt will behave as an acid or as a base. In the answer, we need to check, because this salt is coming from phosphoric acid, which the weak acid will behave as both acid and base. So we need to check, is it going to behave as the acid or base? That will depend on this Ka and Ka2 and Ka3 that we are having. So to remember, before I go to the answer, you need to remember that for each acid, there is the acid conjugate base pair. That means we have Ka and Kb. There is a relationship between Ka and Kb, so we know that the Ka times Kb is equal to Kw for acid base conjugate. For acid conjugate base pair, that's what you have. So let's take an example for HCl before going to our example. If you have, for example, HCl, this is the acid, right? We have the acid and we have the conjugate base. H plus is an acid that has a Ka, which is dissociation constant, and chlorine is its conjugate base, and it has Kb. That means this chlorine we have a Kb. Let's see what will be the Ka. Ka will be equal to H plus times chlorine over HCl. That's the Ka. And remember the chlorine, because it will behave as a base, it will attract the hydrogen from the water and it will be the hydroxide. So that means its Kb will be equal to this one, HCl hydroxide over chlorine negative. Then if you take Ka times Kb, we will see that this one the same as this one, and this one the same as this one. We see that the Ka times Kb is equal to Kw. So this is the relationship between Ka and Kw. The K between Ka and Kb, so we know that Ka times Kb is equal to Kw. For each acid conjugate base pair, we have Ka times Kb, which is equal to Kw. Now let's go to the question that we have. The question was saying, let's examine the salt that was given in the question. This is the salt, right? In the solution, it's in the form of this one and this one. This in the solution, then you need to check, is this one going to behave as an acid or as a base? If it is behaving like an acid, it will attract if it behave as a base, it will attract hydrogen and liberate the hydroxide. If it is behaving like an acid, it will dissociate to give this H plus. So of course this one will dissociate, the pH will depend on how this one is going to be to dissociate. I told you that it can behave as an acid or it can behave as a base. What you can know is that which Ka do we have to use for this one. So we need to check each formation. From phosphoric acid, this is what we have, the Ka1, Ka2, and the Ka3 phosphoric acid, that's how it will be dissociated. But you can see that this salt HAPO4 is coming from the second dissociation. That means here, to solve this question, we use the Ka2 that was given, Ka2 for a phosphoric acid. Then, so if a salt formed from the second dissociation, that means you have a Ka2 is equal to this one, we use Ka2. So that means you have this one and this one. We have acid conjugate base, this is what we have, this one and this one. That's what we have as a mixture. Then this one we dissociate to give H plus and give this one. Then you have Ka value, which we have this one. Then we have also, after having the Ka, you can determine its Kb. Kb, that means this one will react with water to we attract the hydrogen and liberate hydroxide. Can you see we have the acid and the conjugate base, acid the conjugate base pair. So in this case here, we have the Ka, we obtain Ka from the acid and we obtain Kb from this one. Then after obtaining Kb, then you can multiply them. Ka times Kb is equal to Kw, then Kb is equal to this one. Now, as long as you have the K, we have Ka, right? And you have the Kb, then you compare them. So you have the Ka and the Kb. So now, so if you have a Ka and Kb, you need to choose which one is going to dominate. Like for example, this system that will be having from this sort, it will have the Ka, which is equal 6.2 times 10 power negative 8, and it will have the Kb, which is equal 1.6 times 10 power negative 7. When K is higher than Kb, that means more this one will be produced, and you have a dissociation of this one. Now, when Kb is higher than Ka, that means we have more this one, and hydroxide are produced. That's what it means. When you have more Kb, that means you have this one and this one which is produced. That means it is behaving as a base. When you have more Ka, that is this one which will be produced and it will behave as an acid. Here you can see that the Kb is higher than Ka. You can see Kb is 1.6 times 10 power negative 7. So it is higher than Ka. In this case, this one will behave as a base. Kb is higher than Ka, the following reaction will dominate. That means we consider this one as behaving as a base. So it will attract the hydrogen, giving the hydroxide. So now the concentration, we need to find the concentration. So that means what with the concentration, we determine the number of mole. This is the molar mass. That's the moles dividing with the volume of water in liter. Then we get this molarity, concentration of this one is equal to 0.11 mole. That means here we have 0.11 molar. We can then use the IC table. So we have 0.11. Here we don't have, and here we don't have. Then we determine which amount of hydroxide will be obtained after the dissociation. This is Kb that we use, assuming its denominator as negligible. So percent dissociation is equal to 0.1 to 1. That means the assumption is valid. Percentage dissociation is less than 5%, so the assumption is valid. Then you get the X is the hydroxide, which is equal to 1.3 times 10 power negative 4, the dissociated hydroxide. And for us to get H plus, we take 10 power negative 14 dividing with the hydroxide, then you get this one. Then the pH will be negative log of X, which will be equal to 10.1. So the trick here is to make sure that you check whether the salt coming from the weak acid, it is behaving as a base or it is behaving as an acid. And this you will get this information from by calculating the Ka and Kb and comparing the Ka and Kb. If Kb is higher, that means it will behave as a base. And if Ka is higher, that means it will behave as an acid. So that's what you need to do. You need, before doing the dissociation, you need to check whether it will behave as an acid or whether it is going to behave as a base.